This is video 4.5 and it's just some general advice. It's my top 10 tips for working with problems in mathematics, how to get started and how to solve problems. Let's go through them. So number one, make sure you're clear about what you're being asked to prove. So see if you can identify the hypotheses and the conclusions. We've seen some examples where it's not obvious which parts are things you can assume and which parts you're being asked to prove. Make sure you can split those apart. If there are multiple conclusions, then you might like to prove them separately as if they're separate questions or separate tasks for things to prove. If there are multiple hypotheses, then that's good news. That's lots of things that we're supposing in order to make progress with the question. But make sure you can split them apart. If there are definitions of things in the questions, then have a look at the definitions. Make sure that you can unpack them into what they mean. We've seen proofs in this course where you can get through the whole proof just by unpacking what the things mean and showing that those things are all the same. So make sure you can unpack them if you need to. For example, if you see a question about an injective function, then unless you've completely internalized what it means for a function to be injective, you might like to write down if f of x1 is equal to f of x2, then x1 equals x2. Maybe you've got so familiar with injective functions that you can just work with that word, but maybe you might like to have the definition somewhere. And that gives you the chance to recognize perhaps that x1 and x2 match up with something in the question, that you can maybe find ways to piece things together if you write out the definitions for things that you've got. We've also seen that being aware of related definitions is important. So terms that are important might have a definition nearby in your lecture notes or that you saw at a similar time when you were learning about that maths. Other related ideas might be relevant. This is a small one, but if you need to show something for all epsilon greater than 0, then you might start your proof with let epsilon greater than 0 be given. And now you are talking about a particular value of epsilon, so that when it appears in your proof, you have introduced it at the top. This works for other hypotheses as well, but I've chosen epsilon greater than 0 because lots of maths facts start like that. So that's how you might begin your write-up of your proof. If you can't see a way to start from the hypotheses, consider seeking a contradiction, so working backwards, looking at the conclusion and wondering what would happen if this were false. We saw a proof of the IUM inequality where we started by flipping the inequality and then we saw what would happen, what would be the consequences of that. This might give you more things to work with. The conclusions sometimes have more going on, more texture to them. Fermat's last theorem says you have x and y and z and n natural numbers with some properties, and then this complicated equation. If you just start from the hypotheses, we've got some numbers, and try to deduce facts about those numbers until you reach Fermat's last theorem, then that'll take a very long time because there are lots of things that you might write down. You need to have some idea about where you're going and looking at the conclusion that you're aiming for. If you need to show uniqueness, then suppose there are two of whatever and try to show that they're equal. We've seen this quite a few times with x1 and x2. We suppose there are two of them and we show that actually x1 is equal to x2. And that turns up in the definition of an injective function, for example. You can do this in quite a few cases. If you look back at the proof that inverse functions are unique, you'll see that we have two candidate functions and we're trying to show that they're the same function. So this comes up, I would say, whenever you're trying to show uniqueness. Suppose not, and then aim to show that it really is the same thing. Next thing, try looking for extreme or simple cases as counterexamples. Try to look at the edges of possibility space. So I like counterexamples that are very small, have very few things in them to try and make sure that I haven't made any mistakes by making it really easy for me to work with that counterexample. I like checking small values of n. I like sets that don't have too many elements in. I like it if things are disjoint or the empty set. This is why it might be useful to have some really trivial examples in mind, so that when you meet a new object, you've got some interesting examples that you care about, but also some things like the empty set or the relation where nothing is related, where maybe that's a counterexample for the thing that you're trying to prove. So have some extreme or simple things in mind when you approach a new fact. Don't be afraid to mess around, to experiment, but you've got to have in mind what you're aiming for. So if you're not making progress, try something different, maybe closer to the conclusion that you're aiming for, working backwards again, or maybe exploring one of the hypotheses in more detail to see where that goes. It's quite hard to link together hypothesis and conclusion sometimes. That's what makes maths difficult and interesting. And there's some extent to which you might need to try different directions or different ideas. So don't be afraid to change your plan if it's not working out. I find sketches and diagrams really helpful. I think this varies from person to person, but you might use those to help you gain intuition. It's quite dangerous because once you've drawn one thing, you tend to imagine that thing being representative of all possibilities, and often there are multiple possibilities that you might not have immediately thought of. So draw a sketch or a diagram, but try to be aware of what choices you're making. And sometimes that's the whole question, to be aware of the possibilities. Try and draw multiple sketches and diagrams if you can, to do different things. If you get stuck, take a break. You'd be amazed how different your ideas are if you come back to a problem that you'd forgotten about. So if you can't remember what you'd tried already, then you might try something different. Look at the problem again with fresh eyes, and sometimes it's like doing the problem differently entirely. I think the approaches that I use are biased by whatever I was just thinking about or whatever I had just seen. So if I approach it after looking at something else, then maybe my first idea will be different the second time round. Coming back to things. Finally, and I think this is most important, when you have a final proof, reread what you've written. You've been on an adventure, you've thought about lots of things, you've maybe invented some new notation or a word. Reread your final proof and check that the important points have made it into your final proof. Be critical about how clearly you've explained your idea, and check that you're convinced by what you've written, because if you're not convinced, then probably the person you've written it for won't be convinced either. Mathematics often has this idea that you're trying to prove something that you already maybe believe to be true, and at university maybe you're writing up that proof for someone like a tutor who already knows that it's true as well. But the thing that you're practicing is writing a convincing argument, and that means that you need to reread the thing that you've got at the end and check that, as well as capturing the brilliant idea that you've had in the middle, that it also does a sensible job of laying out the details to make sure everything is watertight all the way through. Those are my top 10 tips, which brings us to the end of Introduction to University Mathematics. It's been a pleasure doing these lectures and writing lecture notes for you. I hope you found them useful, and that as you go on to the rest of mathematics at Oxford, that you'll find some of this notation coming up, and you'll remember what it means, that you'll see some proofs, and you'll have seen similar proofs before. I hope you find it useful. If you have any comments about the course, or if you spot any typos, then please do get in touch via the contact email address on the course page. But I wish you all the best with your further mathematical adventures.